Hello. In this video, I'd like to show how we can use OSS-Fuzz-gen to automatically generate fuzzing harnesses by way of LLMs. So OSS-Fuzz-gen is a project that aims at generating fuzz targets for real-world C, C++, Java, and Python projects with various large language models. And they do this by way of the OSS-Fuzz platform. So OSS-Fuzz platform is an open source project that supports continuous fuzzing for open source software. It's a popular fuzzing project that has a lot of open source projects integrated into it. And in this video, I'll kind of assume that you have an understanding for OSS-Fuzz, because OSS-Fuzz is very central to the OSS-Fuzz-gen framework. So in the video, I'll show you a simple example of using OSS-Fuzz-gen on a very primitive code base. Make a few adjustments to the LLM prompts that we generate to show you how you can adjust the output in the LLM generated harnesses. The goal is just to give a little bit of intuition with how things work, and then I will go further in future videos with sort of more detailed walkthroughs of the OSS-Fuzz-gen code. So OSS-Fuzz-gen has a usage MD, and which goes through a bit of some various examples of how you can use it. And the first step is to install the relevant dependencies, which is pretty simple. And then afterwards you have to set up LLM access, which includes either you have to authorize your Google Cloud project, or you have to set some API key depending on which models you use. So OSS-Fuzz-gen supports a lot of different models, and they are kind of, as new models come out, OSS-Fuzz-gen adds support for those. So depending on which model you use, whether you use some that are from the Vertex framework, or whether you use some OpenAI models, you have to set up your authentication accordingly. And I have already done this, so I already have my authentication and model defined. So the goal in this experiment is to go through a simple OSS-Fuzz project that is not yet integrated into OSS-Fuzz, but is a very sort of like is a toy project that we can use for LLM experimentation. And specifically, we will go through this sample that we have here: scripts run new OSS-Fuzz project. And the specific things we will do is we will first have to set up OSS-Fuzz-gen. We have already done that. I have that here on my left side. So we are in the OSS-Fuzz-gen repository. And it's a non-modified repository, with the exception of just a single script that I've added. I'll go more to that shortly. But the first thing you have to do is just set it up. Once you have done that, you just have to run these commands, and these commands will do everything with regards to performing program analysis of the target project that we want to analyze. It will use LLMs to generate harnesses. It will try and build these harnesses, and then it will sort of evaluate the quality of these harnesses against the target code base. So this is where the sort of like core setup is really happening. The core OSS-Fuzz-gen workflow is happening. And in this script here, I have on my left hand side run auto. That is that's exactly the text we have here. So I just copied the script over here. Okay, so let's just quickly run through what this script will do. So the first thing it does is just set a working directory, and then it runs scripts run new OSS project setup.sh, which is the script that we have here. And specifically what this script does is it creates a clone of the Fuzz Introspector open source project, as well as a clone of the OSS-Fuzz project. Fuzz Introspector is a project that can perform program analysis on projects that integrate fuzzing. And the reason we need this is because we need to give some sort of programmatic context to OSS-Fuzz-gen about the program under analysis. And this includes stuff such as we need to identify some interesting functions that we should try and generate harnesses for. And we should also be able to kind of explain the code of our target in a human-like manner. And Fuzz Introspector helps us extract a lot of this program analysis. OSS-Fuzz we clone because we want to, we need to have like a cached version of OSS-Fuzz where we can perform our experiments, such as put in our OSS-Fuzz project. You don't need to do this normally if you run OSS-Fuzz-gen outside of this little toy example. I will go into more of that afterwards. Okay, so once we have set up Fuzz Introspector and OSS-Fuzz, we are going to create a new project in the OSS-Fuzz directory, and this is simply a toy project. So it's a toy OSS-Fuzz project, and this is the specific project that we will be using. As any other OSS-Fuzz project, we have a Docker file, and we have a build sh, and we also have a project YAML. The Docker file sets up the image of our given OSS-Fuzz project, and the only thing we actually do here is we copy the build script and we copy the source and header files into the container that OSS-Fuzz operates on. The build script itself will simply perform a few compilations, and it will compile this charlib.c, and then it already has an existing fuzzer, fuzz-charlib.c, and that's what it will then compile and then link. So in effect, our kind of toy OSS-Fuzz project is composed of a single source file as well as one fuzzing harness, and that's what the toy OSS-Fuzz project does. So let's just take a quick look at charlib.c. Charlib.c is our fake library that we want to fuzz. Let's also open fuzz-charlib.c. So here we have fuzz-charlib.c, and we can see that we have a fuzzer. And the only thing the fuzzer does is fuzz the function count lowercase letters. So if you just look at count lowercase letters, we have that function here, and we can see it takes a C string as input and performs a bunch of basic processing just to test things out. And there's a few print statements depending on what is in the what's in the buffer. But the object file is, so the source code itself, which is like our target library, has a lot more functions in it, as we can see. And the goal of this exercise is to see if OSS-Fuzz-gen will automatically generate a harness for example, this function. So here we have a function called parse complex format. Our existing fuzzer in the toy project doesn't exercise this code, and it's not exercised anywhere within the library itself. So this is an ideal, interesting candidate. We can think of if this was like some type of parsing library. This would most likely be a top-level function that we would be interested in fuzzing. So that's the target library that we are working with, and the goal is to make OSS-Fuzz-gen, or hopefully we will see whether OSS-Fuzz-gen can create a harness and automatically identify this is an interesting function to fuzz, and then also generate a harness for it. So once we have run our basic setup, we set up in our temporary OSS-Fuzz project folder, we create a fake project based on our sample OSS project, and then afterwards we run this scripts, run new OSS-Fuzz project, run project.sh, and we give the name of our toy OSS-Fuzz project as the first argument. So this script here, run project, is the one we have here, and what it does is it first sets up a bunch of environment variables, and these are the environment variables we use to tell OSS-Fuzz-gen what to do. So first we have in our environment, we have a model, which is the LLM model specified. I've already said that. And then what we also tell OSS-Fuzz-gen is stuff such as which heuristics we should use to identify interesting functions in the target project to analyze. So we need to extract information about this function being interesting such that the LLM can generate a harness for that function. And this is what we use. We tell OSS-Fuzz-gen to use these heuristics. So there are various heuristics to extract interesting functions to analyze. And here we have added a heuristic that is far reach low coverage, which tries to pick all the interesting targets in a given project that has a fast static reachability. So like the control flow of the function is large, but it has low coverage. There's also another heuristic that says pick functions with low coverage, but that has some interesting fuzz keywords. So for example, parse complex format here is very likely an interesting, like parse is an interesting keyword from a fuzzing perspective. So first we set up a bunch of environment variables that OSS-Fuzz-gen needs. And then afterwards we are going to launch a version of Fuzz Introspector. First we are going to run Introspector and sort of like we are going to run the fuzzers from our setup. And the whole point is here we are going to build the fuzzers in our OSS-Fuzz Auto Toy project. We are going to build them as a regular OSS-Fuzz project, and then we're going to extract all the program analysis from Introspector so we can use it in OSS-Fuzz-gen. And this is something that's like, this just runs basic OSS-Fuzz commands, and we need that in order to have some type of data about the program under analysis. Afterwards, we are going to launch a local version of what is of an Introspector web application, and the reason we need to do that is because OSS-Fuzz exposes this web app fuzzing introspection of OSS-Fuzz projects, and this web app provides a lot of data about the projects within OSS-Fuzz itself. So for example, we can see data about all the projects, and for example, it provides the program analysis data that OSS-Fuzz-gen needs. So for example, if we say API / far reach low coverage project equals HTS-lib far reach, I think it's but low coverage, we actually get a JSON file out with a lot of program analysis data about this HTS-lib project, which is the one we just looked at, project HTS-lib, and we get a lot of program analysis data out. And this is the data that we want our local version of the web app to expose to OSS-Fuzz-gen, and we need to do that simply because we don't have our toy project in OSS in upstream OSS-Fuzz. Once we have done that, we're now ready to run the LLM generation, and that's what we do exactly here. So at this point, we are going to run the OSS-Fuzz-gen core, which will take all the program analysis data, start to use that data to formulate LLM prompts that we can then pass into our model, and the model will then shoot back some suggested harnesses, and there is a bit of conversation going on, such as trying to improve the harness and various things, but that's exactly what we'll do at this point. Once this is done, OSS-Fuzz-gen core will launch. We will be able to launch a web server from OSS-Fuzz-gen core that will display all the results. So I'm going to just run this script, and we can see the sort of like workflow of it. And once it's done, we're going to digest the results. So here I have copied in. So in short, what we are going to do now is we are going to run all of these things. And once we have done that, we will look at the results. Once we have seen the results, we are going to try and adjust the way we make our prompts to see how it reflects in the generated harnesses. Okay, so let's first run all of this. It's not going to take too long. So first we are, as I said, we are setting up a Fuzz Introspector version locally, and we need to have this because we need to launch the web app. We are going to, now we are doing the running of the fuzzers in our OSS-Fuzz project in order to extract all of this program analysis data. So we are collecting code coverage information as well as extracting static analysis information. And now we are running the introspector analysis on our target project. And that should be done in a moment. So this is some things that are happening within the OSS-Fuzz container now. And now the introspector analysis is done. The web app has actually launched now, so we could try and navigate to localhost 8080. And now we have our the version of our local web app where we have our OSS-Fuzz Auto, which is the project we set up. So let me just go back here, which is the OSS-Fuzz Auto project we set up. So we can see that there is actually kind of the web app running where we can do APIs such as equals OSS-Fuzz Auto, and it returns, for example, here we can see all the data that it returns, and that includes an interesting target here, parse complex format. And you can see all the data that it has, such as it has the source code information, which like we're in the specific source code file. This is the file, this is the line numbers. We have such stuff such as the types of the function that it accepts and that it returns. We have cyclomatic complexity, which is here. The accumulated cyclomatic complexity is 61, and so on. So this is working well. And now OSS-Fuzz-gen is running on the left. All of these printouts here come from OSS-Fuzz-gen itself. And we can see that OSS-Fuzz-gen has now launched a web server at localhost port 8012, and this web server now will hold our resulting report. So let's take a look at that. Here we have the results from our analysis. We can see we have one benchmark here, and benchmark is the sort of target. We were a target function that we tried to make a harness for. We have some stats for it, such as the build success rate, whether a crash was found, and we also have information about the coverage gains and more. So if we try to click on this, we have the report for the analysis of our OSS-Fuzz Auto project, and in this case the parse complex format function. So the important bit here is this is our project, and this is the target function that we tried to analyze, and we have generated two different harnesses for the function. So we tried to call the model twice to see if we got different results. So the prompt itself are shown here. You can see that it says something like you're a security test engineer who wants to write a C program to discover memory corruption vulnerabilities, and more, and so on and so on and so on. And this is all of the text that we actually gave to the prompt initially, to the LLM model initially, and it just has a lot of stuff. It has existing harnesses as an example. It has description about the like the format that we want the fuzzing harness to be. So we tell the model that we want it to be in LLM fuzzer test one input format. And if we look for whether we should also have some information about the sort of function under analysis. For example, we say here that your goal is to write a fuzzing harness for the function on a test. And here we have the function signature of the function that we want to analyze. And that's sort of like a short walkthrough of the whole prompt. So if we look at one of the samples that were generated, we can see the final code that was created by the harness is shown here, by the models were shown here. So the reason is we do several iterations. So first, the result from the initial prompt here in the first run on sort of like model interaction was the following LLM harness. So first, this harness was generated. We can see that we have a fuzzer here. It casts the input harness buffer into a char string, and then it passes that directly to the parse complex format. And we can see from OSS-Fuzz-gen tried to build and run this harness, and it built fine, but it ran into an issue in the stir-length function when calling parse complex format. So the harness here calls into, you can see the stack trace LLM fuzz test one input, and it calls into parse complex format, which happens here, but it ran into a stir-length issue. And the whole problem is here that parse complex format actually expects a null terminated string, but the harness created, the model created a harness that does not have null terminated values in the string, or like in the buffer passed into the target function. So what OSS-Fuzz-gen core then did was it took all these, errors, it took this source code, and it then asked the LLM again, hey, could you try and fix this harness, basically. Came up with various ideas on how to do it, and after that, we got a new harness that looks quite similar to the existing one, and there was yet another iteration, and in the end, it's sort of like the iterations just follow through until OSS-Fuzz-gen core or has reached something that it's satisfied with, or whether some sort of max number of iterations has been reached. And in this case, the final code that we got from OSS-Fuzz-gen core is here, where we can see that we correctly allocate a new buffer with size +1 of the buffer as input to the harness, and we then the harness then null terminates it as well before passing it into parse complex format type. So this harness here is the exact one that one would essentially write for the parse complex format. So it's perfect in that case. Although it's very simple, it's a perfect harness for the parse complex format function. And yeah, that worked indeed well. And we can see also at the bottom, we can see runtime logs from the harness showing how it ran for a number of seconds, for 31 seconds in this case, and there was no errors detected. Okay, so that's kind of like the short story of how OSS-Fuzz-gen core. There's a lot of preparation before getting to the prompts in terms of program analysis. And then the prompts is everything you see here, and there's a lot of interaction between OSS-Fuzz-gen core and the models, because it's not a single prompt. There's a lot of back and forth. And finally, what you get out is a harness, and in this case, multiple harnesses with that were generated by the models. Okay, so now let's try something interesting and adjust the way we do prompts to see if we can sort of impact the way the harness looks afterwards. So I'm not going to go too much into the details with the source code of OSS-Fuzz-gen core in this case, but in short, in LLM Toolkit Prompt Builder, we have the logic that assembles the prompts for our that takes the program analysis, converts it into prompts, and passes passes these prompts to LLMs. We have that in LLM Toolkit Prompt Builder. And in this experiment, we used the default prompt builder. We have a lot of different prompt builders around. So there's 5 different ones. We have, for Java, Python, there are some specific ones for C, and we also have, there's also a prompt for converting test cases to harnesses. But anyways, we have the default prompt builder here, which is the one we want to use. And we can see here what it does is it loads a lot of TXT files, and these TXT files are the template prompts that we that template text for the prompts that we want to use. So in this case, I would like to adjust 2 of these templates to add some more context in our harness. And the specific one we want to adjust is priming.txt, and then also fixer instruction.txt. And these exists inside the prompts/template XML folder. So let's find the priming here. We can see that it has stuff such as you are a security testing engineer who want to do some stuff. And if we actually search for this in our prompt, we can see that that's the exact text you have here. So let's try and adjust this TXT file, and then say down here, we want to have a final thing and says, finally, the most important thing in the harness is to include a comment saying, hello from YouTube, auto harnessing is pretty cool. And please include this comment at the top of the harness. You must include this. Let's try and be a little bit forceful. And let's also adjust in the fixer instruction prompt here, as that's the prompt we use for fixing things around, like for the iterations afterwards. Okay, so now we have adjusted the templates, so let's rerun our experiment. Okay, the experiment is now running, and in a moment we'll see the differences. Okay, so it has now finished the running of it, and let's see the difference in results. So still very simple, very similar to before. And if we click here, we can scroll down and look at whether our comment is. So where would it be? Okay, so here is our comment right here. Finally, the most important thing in the harness is to include a comment saying etc. etc. So indeed, our instruction was added to somewhere in the whole assembled prompt. So the main point is here OSS-Fuzz-gen does a lot of assembling from many different parts to generate the full prompt, and we can here see the comment that we added. So let's see if this was reflected in the final harness. So if we click into here, we can So first, let's see here the first iteration. We have the code here, and we can see that indeed there was a comment added by the model into the harness. Hello from YouTube, auto harnessing is pretty cool. We then, this harness didn't run into the same issue as before with a non-null terminated string passed to the target function. And we can actually see that we did include in our fixer prompt as well the comment on add this, or like our text for adding in this comment. And indeed, the harness again added, the model again added a comment into the target code. And for some reason, the comment is not placed in the final code. and that's very likely just because it was like got phased out or similar from the prompt. But we can definitely see that it was reflected in the first initial iterations, and it came through in that way. We can check the second example and see if it came in there. And indeed, in the final code of our second example, we have the comment. So this was added to our harness. The model added the comment in, and in that way we can actually see how easy it is to impact the outcome of the model. So for example, one thing we could try and do is we could add some textual constraints saying, don't try and pass buffers in that has non-null terminated strings, and that might have an impact on the results. So at this point, I think I will stop this video, summarize it up, and in short, we have done a quick walkthrough of OSS-Fuzz-gen, how to use it for generating harnesses for a very simple project, and we saw how we automatically identified the largest, most complex function in the target library that is suitable for fuzzing. OSS-Fuzz-gen also took that information and a lot more information, put it into a context that LLMs can understand. So human language was created to it, and OSS-Fuzz-gen also OSS-Fuzz-gen also tried multiple times using LLMs to fix the source code, to make it run proper, to not stop at the first time we see a false positive in terms of running into a Sterling issue, and so on. So I think that's a short introduction to OSS-Fuzz-gen. There's a lot of stuff involved into it, and I hope to make some follow-up videos where we go into a bit more detail of some more narrow parts of OSS-Fuzz-gen. But hope you liked it. Have a good day.